Okay, so today we're going to talk about Wick's theorem. Just as a quick recap, we've been focusing on 2 to 2 scattering. Our initial state was symbolized like this, a particle of momentum energy P1 and another particle of momentum energy P2, and this is the Ket representation for what's going on physically when we have that as our starting state that we introduce into our collision chamber. And we can express that like this using relativistic normalization as we talked about before. We want to calculate the chances of measuring two particles at the end, but of momentum energy Q1 and Q2 after the interaction. And the interaction we're using for our toy model for scalar field theory, which is what we've been doing so far, is the following, where we call it phi-fourth theory, where we have these other factors, but basically our interaction term is phi to the fourth power. And remember that we also had to normal order it to get rid of some of the infinities as we talked about in first and second order, in zeroth order and first order scattering terms that we calculated in the previous lecture. Dyson's formula, recall, gives us the final state after the interaction is complete for any given initial state. And the form was like this. If we have our initial state here of P1, P2, and we want our final state after the interaction is complete, there's this operator U that we just apply to our initial state, to any initial state, and that will give us our final state. And U, we showed according to Dyson's formula, is the following. It's an exponential, which is really a sum, an infinite sum of various terms of this form over here. And remember that rather than use this entire formula acting on this initial state and then writing down our full final state, which we call psi final, we usually in this business directly calculate the transition amplitude we're in, which means we just have to take our answer that we get here, U of acting on P1, P2, and then just project it onto the specific Fock state that we're interested in to see our final state, and that's Q1, Q2. We take the bra of this over here, and that's called SFI, the transition amplitude to go from here to here after this interaction is complete. U, when you expand it, is this over here. And then when we project it, when we act on the P1, P2, that's this over here. And then when we project it on Q1, Q2, that's this over here. And if we just follow through our formulas, that ends up being this over here. The term that we talked about calculating this term and this term, the so-called zeroth order and first order terms, we did that in the previous lecture. Now we're finally going to be interested in calculating this, the so-called second order term. And the order refers to the order of lambda. So this term over here, this is really what we're interested in calculating. The big problem here, the reason we didn't go over it in the previous lecture, is this t. And this t, recall, is the time ordering operator t. Practically speaking, it's difficult mathematically to deal with time ordering directly. And then that's the purpose of this lecture, that luckily a guy named Giancarlo Wick discovered a better and more elegant way, which is called Wick's theorem. We're going to get to Wick's theorem, but first some mathematical preliminaries. The mathematics gets more dense and more intense, but I'll try to continue to go step by step, and don't get intimidated by it. We're going to have a purpose to everything we're doing, but we're going to first start with the following definition. We're going to define this thing called delta sub f, which is called the scalar Feynman propagator. The Feynman propagator, and in this case, we're just still talking about scalar fields. We'll talk about that for spinors and things like that later on. But for now, this is the symbol of it, and it's a function that will shoot out a number, and it'll input two real numbers, but the two real numbers themselves are not actually real numbers. They're 4 vectors. So here's x, which is a 4 vector, and y, which is another 4 vector. And turns out that what shoots out of this function is actually really only dependent on the difference between these two 4 vectors. So x and y actually represent 4 vectors. So technically there's 8 variables here that go into this. And it's the difference between the two that gives us our final function. By definition, the scalar Feynman propagator is this expression here. This is, if you say it in words, the time-ordered expectation value of phi of x and phi of y. So what does that mean? Well, we take an operator phi of x and phi of y, and we multiply the two, which means you apply this operator first and this operator second. But when you do the time ordering of it, it means that whichever one of these has a time value that's less, that goes to the right. That's what this time ordering function does. Technically, there should be a bracket here and a bracket there. And then once we do that, we get an operator, and that operator we act on the vacuum state, which is called 0 here. And then we get a new state, and then we we project that onto the vacuum state with this bra over here, and that gives us ultimately a real number, and that's the scalar Feynman propagator. Now, by definition, when we say time ordered, this is what we really mean, as I just mentioned in words, that if it turns out, remember that this is a 4 vector, meaning it has a time part, which is x0, and this is a 4 vector, which has a time part, which is y0, and then it has 3 spatial parts, and this has 3 spatial parts. If the time part, which is x, in this case superscript 0, is greater than y superscript 0, meaning that y is actually taking, these are space-time points, x and y, so they have 4 dimensions. If y itself is earlier in time, then we always apply the y first to the right. This is still stays phi x, phi y. But if x, it happens in earlier time, meaning x naught is less than y naught or y naught is greater than x naught, then we have to switch the order so that the earlier time operator gets put on the right. That's what the time ordering operator does. We have to switch the order of the two. So that's the definition of the scalar Feynman propagator. And it will use 2 different calculation methods depending on whether x is first earlier in time or whether y is earlier in time. Now, for the previous lectures, I really used the discrete representation of things to be more consistent with quantum field theory books so that you can follow along in other books and to do what a lot of the other books do. We're going to now go back to the continuum representation, which we talked about but didn't often use for calculations. But we're going to start doing that now to be more consistent with these other QFT books, which I want to be able to have you go and jump to and read after you finish these lectures. So this is the continuum representation for phi of x. This is in the interaction picture that we talked about extensively. So this is our formula that we kind of wanted you to memorize, both in the discrete form and in this case in the continuous form. So phi of x is this, which is it's an integral over d third p of destruction operators, a sub p, e to the minus ipx, plus integral over d3p is a summation of creation operators, a dagger p, e to the plus ipx. And remember, this p here should really have an arrow over it. This is a 3 vector, as is this, because the integration is just over the 3 vector, the 3 components of p. But this p over here is a 4 vector, and px means the dot product of p with the space-time 4 vector x, as we've talked about before. Now we're just giving a name to this part of it and this part of it, and we're going to call the name for these collection of destruction operators phi subscript minus sign in parentheses x. And this, with the creation operators, we call phi plus parentheses x. Take note, traditional QFT books actually reverse this and talk about phi minus referring to the a daggers, which has come out confusing, and the phi plus referring to the a minuses, and they use superscripts rather than subscripts. Here, by using subscripts, hopefully that shows a different notation, but be careful. A lot of the traditional QFT stuff does it opposite, which causes actually some confusion. Schwichtenberg's book, which is a good introductory level text for understanding a lot of what we're talking about, does it this way, which is why I also started doing it this way to help avoid further confusion. Although it will be somewhat inconsistent with some books. But just notice the subscript rather than the superscript. So the minus refers to the destruction operators, the way we're using it, and the plus refers to creation operators, the way we're using it. Now let's just suppose the first scenario is true, that when we input this function that x naught is greater than y naught, which means that y naught happens at an earlier time. Well, then this thing is already time ordered, meaning that the earlier space-time part is on to the right. We just look at the time part of the space-time part. So we just use this top formula over here. I'm just going to expand things, that this is just equal to phi plus plus phi minus. And this thing here is equal to phi plus plus phi minus. Then I'm just going to use FOIL, which is first, outer, inner, and last, just to expand these two binomial multiplication. So I get the first and the first right here, the first and the last over here, the last and the first over here, and the last over here. And of course, this is still sandwiched between the inner product from the vacuum states. That's what I get here. Now look at this a little bit more carefully. look at this term over here. Here I'm going to have just a bunch of destruction operators. Remember, 5 plus is, sorry, I apologize. Let's first start looking at the simpler term, this term over here. This phi minus is going to have a bunch of destruction operators. Any destruction operator, remember, this is going to be over the gamut of p's, in this case, continuous representation, so all the different possible momentum, 3 momentum values p. Every time, no matter what p is, I have a destruction operator, a sub p, acting on the vacuum state, I always get 0. So that's going to kill this whole thing. So this term goes straight to 0. Let's look at the last term, and the same exact thing. I have 5 minus y. These are all a bunch of destruction operators, this time with the space-time point y. And whatever a sub p is regarding, I'll go through the whole range of it when I integrate this, it'll always kill the vacuum state. A sub p kills the vacuum state, so this will be 0. The first term is a little bit different. Here I have a creation operator. So when I have a creation operator, which these are a collection of creation operators over here, phi plus, the way we're using it, is a creation operator. So I'll get a whole collection of different states here of all different momentums, P1, P2, P3, P4, but which is not 0. But then when I hit that again with another creation operator, which is this over here, I'm going to get another state that turns the vacuum state to a 1-particle state and then a 2-particle state. So I'll have things like, momentum P1, P2, P7, P85. And then when I have that, that's what I show over here, I'll have something like this, P1, P2, but then ultimately I have to take the inner product of that with the vacuum state. And these are all Fock states. So if these are not identical, this equals 0. So if I have any 2-particle state, regardless of what the 2-particle state is, when I take the inner product of that with the vacuum state, I will always get 0. So that's what this is over here. So these 3 terms in this expansion will always give me 0. This is the only term that's going to survive. So when I take this scalar Feynman propagator, this delta sub f, and I define it like this, supposing x naught is equal to y naught, I really just get this over here. So that's the summary of this, when x naught is greater than y naught. Similarly, if I had the opposite situation, that y naught is greater than x naught, you can do the calculation, but it'll show you almost the same type of thing, that I will get these things reversed. That this scalar Feynman propagator, when y naught is greater than x naught, will just be the same thing I talked about, reverse, meaning that the y gets put in here and the x gets put in here, but I still have the minus here and the plus over here. Thus, I can say that using my definition of the scalar Feynman propagator, which was this over here, when we calculate things out, this is actually what happens. That if x naught is greater than y naught, I can just say that this is what I get for my scalar Feynman propagator. But if y naught is greater than x naught, this is what I get over here. I get a vacuum expectation value of this part, the phi minus part of x, and then the phi plus part of y, if x naught is greater than y naught, but I reverse the x and the y if the opposite is true here. So this is another way to write the scalar Feynman propagator when you do this calculation. We're also going to note the following, just bear with us. This is all eventually going to make a lot of sense. It just seems like a bunch of math that we're doing for who knows what reason right now, but it has a big point. That here, this is the expression. Remember, this is the case when x naught is greater than y naught, or y naught happens at an earlier time. This is that part of the expression. We're going to reformulate this a little bit, that if I have this expression here, it's equal to the same thing, minus 0, of course. Anything minus 0 is itself. But another name for 0 could be this, where, remember, this expression here that I just wrote out equals 0. But why does it equal 0? Because I have phi minus, which is the destruction part, acting on the vacuum state, which is always 0. This is an integral or a sum over a bunch of destruction a sub p operators, but any of those acting on this will kill this. So I can rewrite 0 as this another fancier name for 0 over here. And that's what I've done with this expression. Now it's equal to this. But now I have the inner product. I can take out the inner product and just look at the middle part and kind of factor things out. So now I can use the inner products, bring them out here, and just take these 2 operator terms in the middle, which is over here. Take a look at that. And now this here is this operator times this operator, just phi minus, phi plus, minus phi plus, phi minus, and the appropriate x and y's that I'm not mentioning, but you can see. But this really is nothing but the commutator of, that's the definition for the commutator or commutator of these 2 operators. So here's what I express it as here, phi minus x, phi plus y. So this expression here, which we started with, can actually be shown equal to this right over here. And then I'm going to show it in a little bit later, but this commutator turns out, even though it's the commutator of two operators, it turns out that this commutator itself just turns out to evaluate to a simple number, not a whole operator. And if that's just a simple number, you can pull that out of the inner product and just have the commutator itself. And we'll show that a little bit later, because once you pull that out, then zero inner product with zero, the vacuum state inner product with itself is by definition 1. So we're going to get to exactly why this is a number, but for now, just assume that. We'll show that shortly. So what to remember now is that this entire expression here, it can just be shown equal to this commutator over here, which is just a number. And similarly, you can do the same thing for the opposite expression. This is the expression we got when y naught happens at an earlier time, but this is the expression we got when x naught happens at an earlier time, almost the same thing reversed. And we can show, just using the same argument, if you want for practice, do it yourself, that you get this commutator over here. So now we're going to go ahead and actually numerically calculate these terms. This thing over here, we just showed that this is really the same as a commutator, but we're going to kind of plug in what these things are and actually grind it out and actually calculate this over here. This is ultimately going to help us calculate this entity called the scalar Feynman propagator, which still, I didn't give you the purpose of it yet, but we'll go over that. It has a big purpose in QFT, which we'll show. But for now, we're going to crank out some more math and actually calculate this thing over here by plugging in numbers. So here we go. Remember, just again, the scalar Feynman propagator is this expression over here when x naught is greater than y naught. So that's the expression we're about to calculate. And let's start doing that. Now, remember what these things mean. We talked about the continuous representation, which is what we're going to do. And in the continuous representation, this phi minus of x is all the destruction parts, which is a sub p e to the minus ipx. And it's the integral over dp to the third over 2 pi to the third of this over here, of these terms, ap e to the ipx. That's where this thing is. And this part here, the phi plus of y, is the same type of thing, but for the creation operator. So that's where the a dagger sub p prime e to the plus I p prime y comes in. That's from over here. And there's a y here, so a y here, and this x is x here. And this is the integral. I just have to change, because these are two integrations going on, I have to change p to the dummy variable p prime over here. So d third p prime over 2 pi to the third, and that's this guy over here. And then I've already done some of the work, skipped a step or two, and then left the operator stuff and the exponential stuff here, and pulled out of the inner product here some of these terms over here, the integrals, and these factors of 1 over square root of 2 omega pi and omega p prime, of omega p and omega p prime. So that's what this thing here is. This is just using that continuous definition that we talked about before, re-expressed over here. Now, just keep cranking things out. I can also, of course, factor out the e to the minus ipx and e to the plus ip prime y. These are numbers, not operators, so they can be taken out of the inner product like we've talked about before, which is what I did here. And now I just have this inner product of operator ap a dagger p prime. But now remember, there's a commutation relationship that we spent a lot of time deriving a few lectures ago. There's a discrete form and a continuous form. We talked about the discrete form, but if you look back at those lectures, here's the commutation relations for in the continuous form. And the commutator of AP, a dagger P prime, is equal to 2 pi to the third delta to the third P minus P prime, this over here. So I can use that commutation relation to change this and reverse the order of these two guys, as long as I add the commutator of it, which is this. Just going through the math here, you can take a pen and paper and do it. We've done a lot of these similar types of calculations before. We're just using the continuous representation here. So this thing this whole thing here is repeated here. Now this thing, instead of here, I change the p and the p prime over here, but I have to add the commutator of that when I do that, which is this over here. So that's what I get. Now the advantage of doing that is that now I'm going to have two different inner product terms added together. 0, this, 0. And then the other 0, this, 0. These are inner products. And when I do this inner product, I have now AP acting on the vacuum state, and as we talked about several times already, that's going to get killed, and this is effectively going to be 0. So what's going to be left is this guy over here, and then eventually this is a numerical term, 2 pi to the third delta function, which just gives me a number, not an operator, and I can pull that out of the inner product, and knowing that the inner product of the vacuum state with the vacuum state is 1 gives me this. So this whole thing will knock out and just simplify to this over here. Now I have a delta function, a Dirac delta function of p minus p prime, and an integral over dp prime to the third dimension, and this is to the third dimension. So now just knowing the properties of the delta function, which hopefully you recall from undergraduate quantum mechanics, which is kind of a prerequisite for what we're doing here, I could integrate over the delta function, and this is the formula here, that if I have an integral over d third p of Kronecker delta function of p minus p prime, then I will get, there's just so you know, there should be arrows here and here, here and here and here and here, if you just follow that carefully. But I should get, when I integrate over the delta function, I'm just going to sample the function at point p. So this formula should be pretty familiar from quantum mechanics, that if I do the integral of f of p delta function p minus p prime, I just get f of p itself. And then this whole integral collapses down to f of p. So when I do this delta function, this is the property of delta functions here, this integral over d third p prime with this delta function of p minus p prime is going to force every one of these p primes to be equal to p. And this is what I'm going to get over here. The scalar Feynman function of x minus y is equal to this. This integral still survives. Integral of d third p over 2 pi to the third, 1 over 2 omega pi. Why? Because this omega p prime becomes omega p, and that's the same as this term. And then when you do square root times the square root, you just get the non-square root term. So that's where the 2 omega p comes from. And this still stays e to the minus ip. This p prime becomes p, and then that I can have e to the minus ipx, e to the plus ipy, and the p's can be factored out. The minus ip can be factored out, and then I just get x minus y. So that's what just shows that this scalar Feynman function gives me this over here. When x naught is greater than y naught. So that's this over here. This is a pretty important calculation here. And there's an analogous result, of course, when y naught is greater than x naught for the other situation, which I have represented here. So here's the scalar Feynman propagator. That's equal to this over here when x naught is greater than y naught, but when the order is reversed, then it's this over here. And this is, of course, the starting definition for the scalar Feynman propagator. This over here, the time ordered expectation value. So this is what you get. There's a bunch of nomenclature here that we'll keep defining and redefining the same types of things, is the way a lot of the books do it. And I'll try to keep it somewhat clear, but just pay attention to it. This is the original definition of the scalar Feynman propagator. When we calculate everything out, we get either this or this, depending on which is earlier in time. And when y naught is earlier in time, we keep the order, and if you calculate this whole thing out, you get this term here. This term here, which is a number, a complicated number, a complex number, you will just define as this d x minus y, just as notation. This is taken from David Tang's QFT notes. But with the same expression when the y and x are reversed is called dy minus x. So that's this here, and that's what you get when y naught is greater than x naught. Now, you can play around with these calculations a little bit, but you can also just directly look at this commutator, which comes into play, and just calculate using the same formulas we did before exactly what this is without going backwards. You can just look at the commutator of these two. And remember I said before, the commutator of these two actually gives us a number, and this is just a proof showing the same thing. It's pretty much the same calculation, just with a few different terms spelled out here. Remember, again, this is a continuous way of expressing phi of x. And then if you just put the commutator formula into that, you take the commutator of this, the commutator of this. Remember, the phi minuses are the destruction operators, the phi pluses, the way we define it here, are the creation operators, and you still have all these integral terms. We use these dummy integration value rule p prime because we have two integrations or two sums going on here. And then when you do the commutator, you can pull out all the non-operator stuff out front, which is what we did, and just leave the commutator of these two terms. But as we talked about, we know the commutator of AP and A dagger P. We spent a lot of time deriving that earlier in our QFT lectures. And at least in the continuous form that we just showed on the previous slides, this is just the delta function. And then you see you can still have this delta function of P minus P prime stuck within this over here, this integral over here. So that's going to just sample this whole thing and force every P prime to equal P. And that's what we get here. And then that just shows this commutator directly as D x minus y, the same formula that we saw before. This is the direct formula for the commutator. This also shows that the commutator, as we talked about, is really just not an operator. The commutator of these two things actually has just some numerical complex function. So kind of to summarize, there's a lot of definitions going on here and a lot of math. There's different ways of stating this, but we started off with this definition that the scalar Feynman propagator is a time-ordered expectation value of time-ordered vacuum expectation value, which is what this really is, of phi x, phi y. And then cranking things out, we found that when x naught is greater than y naught, then you get one answer up here, but when it's the other way around, when y naught is greater than x naught, then you get this thing over here. And this thing over here is dx minus y or dy minus x, depending on which of those scenarios you have. And that really can also just be summarized as a commutator of this subfunctions phi minus and phi plus. And in this case, it's this phi minus y and phi plus x. And then remember, this dx minus y is just the expression, is this expression here, which is a numerical expression. It's an integral, but there's no operators in here. And similarly with y minus x, the same thing with y and x reversed. So just a bunch of nomenclature. Worth probably taking a look at this slide from time to time. Now, what does all this have to do with what our original goal was, to try to solve the second order term S2 in our scattering, 2 to 2 scattering problem? Just to remember, again, this is the term we were trying to initially solve, and we had this time-ordered issue here. What does everything we just did have to do with that? Well, I'll show you now. I'm not going to prove Wick's theorem, but I'll give you an idea just with just two operators, what it is, and then you can look up your own proof, but it gives you at least the flavor for why things are probably going to be true. We have to deal with time-ordered terms in our S2 calculation, as you just saw. Let us start, instead of looking at that whole S2 term for a 5/4 theory, let's just look at a simplest type of time-ordered term, this. Let's just say we have an operator phi of x and an operator phi of y, and we wanted the time ordering of these two. First, consider the case, remember this is an operator, this is an operator. Consider the case when y naught is an earlier time than x naught. So in other words, that this already is time ordered the way we write it. Consider that case. Well, then the time ordering of these two operators is just these two operators without changing them, because they're already considering only the case where y naught is already earlier, and that's why it goes to the right. That's what this equality is true. And now I'm just going to expand these using their definitions, phi plus plus phi minus, and this one too, phi plus plus phi minus. And now again, use the FOIL technique, first, outer, inner, last. That's what I get. Now look carefully at this over here. I'm going to just play a little game here. I'm going to use this term and just keep it over here. This term and keep it over here. This last term, just keep it the same over here. But look at this term over here. I'm going to manipulate this a little bit and say that I'm going to switch the plus and the minus. The plus, which remember again are the creation operators, and the minuses, I'm going to switch them. So I put the phi plus here and the phi minus here. I can't just do that in quantum mechanics or quantum field theory because these are operators, they don't always commute. So in order to account for that, I always add the commutator of the two over here. And that you can just follow along here, that the commutator by definition of these two is this minus this, which means that this term itself, phi minus over here, is equal to these two things switched plus the commutator. So that's why I can just replace this with its equivalent sum over here. That's how I got from this line to this line. Now take a good look at this. If you look at this line just before it, technically each of these are so-called normal ordered. If you remember, normal ordering means that it's different than time ordering, but normal ordering means that all destruction operators are to the right. So in this case, there are no destruction operators, so there's nothing to switch. There's only creation operators. Remember, plus and plus are creation operators. So we're nothing to do if we know. This is already normal ordered. This here is already also normal ordered because this has the destruction operators here. So this technically is also normal ordered. This term here is also normal ordered because you have destruction and destruction, and they're already destruction. So all the destruction operators are already to the right as much as they can be. This part was not normal ordered when we did this expansion, but using this, we can re-express it as this. And when you look at this, I have this, 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 and this, and at least these three terms now are normal ordered. These other ones were already normal ordered, but this thing, when I flipped it around, now is normal ordered. The price you had to pay those in order to make these two whole expressions equivalent, when I forced this to be normal ordered, I had to add the commutator of these two things over here. But remember, from all that cumbersome calculation we just completed, the commutator of these two things is nothing but this number or numerical expression, which we're calling df x minus y. So what we've learned, at least in this scenario, when x naught is greater than y naught, is that the time ordering of these two operators, phi x and phi y, can actually be changed to the normal ordering of these two operators, plus this part of the scalar Feynman propagator, which here we just call df x minus y, because this is just the part case x naught is greater than y naught. So if you look at this without getting into a full proof, it just shows you that we can change time ordering, which is hard to deal with mathematically, into normal ordering, plus some scalar Feynman propagator or a part thereof. This gives you an idea for what we're about to go over with Wick's theorem. And then similarly, if we looked at the other case where y naught is greater than x naught, we have a similar thing, except we have df y minus x. So what we found then, and if you recall the definition, delta f actually includes two different scenarios. When x naught is greater than y naught, we get this, which we showed before, df x minus y. And when y naught is greater than x naught, then we get this over here. That's what we've done, and we've defined this as followed and show that the calculation gives us this. So using that, we've kind of re-expressed this whole situation as follows, that regardless of whether we're talking about x naught comes earlier or y naught comes earlier, the time-ordered expectation value in all cases of this two-operator product is actually equal to the normal operator of this two-operator product, plus the scalar Feynman propagator. So this is what we've learned over here, that the time ordering can be re-expressed as normal ordering plus the scalar Feynman propagator. This is just for the case of two operators that are multiplied together. This is really the essence of Wick's theorem, which I'm going to express in a more general form in just a moment, that you can change time-ordered products into normal-ordered plus scalar Feynman propagators. More nomenclature of kind of just different ways of expressing the same thing, but stuff you need to know for QFT. You may want to take time and go back and write some of this out yourself. But another way, by definition, of writing the scalar Feynman propagator is this. If we have the scalar Feynman propagator of x space-time point x minus space-time point y, we can just write the operator phi x and phi y and just put this line underneath them connecting the two, and that's called a contraction. So a contraction, by definition, of these two operators, phi x and phi y, this is operator defined at space-time point x, another operator defined at space-time point y. By definition, the contraction of those two is just the scalar Feynman propagator, which we've defined itself and calculated itself. That's what contraction means when we put this line or bar connecting these two. Thus, for the above, with that two-operator expression, we can just say that this is the new thing that we've proved, that the time-ordered expectation value of phi x, phi y is just the normal ordered of that same thing, plus the contraction of the two. These are just different terminologies that we've done so far. We're not going to fully prove Wick's theorem. You can look it up yourself on in different sources, but this may give you a hint as to why it's true. Wick's theorem is pretty much what we just said, but it applies not only for two operators, but for any number of operators. So let's just say we have a whole string of operators, phi of x1, phi of x2, phi of x3, phi of x4, so on and so forth, where in this case we're just using the same family of operators, but remember at every different space-time point, this is technically a different operator at x1, then x2, then x3, then x4. So the time ordering operator, the time ordered value of all of these operators can be re-expressed according to Giancarlo Wick and Wick's theorem as the normal order of all of these things plus the normal ordering of all possible contractions of these. Now let's look a little bit carefully what that means. This is Wick's theorem. Instead of time ordering, I change this to normal ordering of this entire expression with no contractions inside of it. Plus, I start to do all different combinations of contractions. So on this first line, I just contract two different operators and leave the rest the same. So I have the contraction of this and this and leave the rest the same. And then I can also contract x1 with x3, which is what I do here, but I leave all these the same. These contractions, remember by definition, equal to delta f x minus y, which depending on x naught or y naught will be equal to that df expression, which is just a number. It's not an operator as we talked about before and we've calculated before. So this actually ends up being a number. These are still operators. But then when I use Wick's theorem, I still have to use the normal ordering for every one of these because these are operators. So this normal ordering still applies to every one of these other operators that are not contracted. But there's more to Wick's theorem. I don't just do one contraction and consider all possible cases where you only have one contraction of two terms. I also have to consider the case when I use Wick's theorem of two contractions. So here in this case, I contracted x1 and x2. In this case, I did x3 and x4. And then if there's any other operators, they're unchanged. But then I have to do x1 with x3, all possible ways I can contract these things, and x2 with x4, and then keep everything else the same. And the normal ordering is that these will end up being numbers, these contractions, so there's no meaning for normal ordering numbers. But there are other operators potentially here that I keep normal ordering, plus so on and so forth for all possible contractions. If this string goes on more and more, then I would do all three. I would contract 3 different contractions in here with 6 terms, and 4 contractions and 5 contractions, so on and so forth. But this is Wick's theorem. It says that the time ordering can be changed into normal ordering plus all possible contractions, and the normal ordering of all possible contractions. So just to have an example, this is almost like the previous example, except I'm just cutting my string off at 4 operators, just to go over it again. And instead of just, it gets exhausting writing this stuff. So instead of writing phi of x1, which is this operator at spacetime x1, sometimes we just write phi of 1. That's what that means. You'll see this in a lot of books. So I can just change this. If I use Wick's theorem, this time order I can change to the normal ordering of all of this stuff with no contractions, plus the normal ordering with 1 contraction. And the 1 contraction I could pick, I can contract these 2 terms, phi 1 and phi 2, or I could do phi 3 and phi 4, and so on and so forth, or phi 1 and phi 3, or phi 1 and phi 4, or phi 2 and phi 3. I can figure out all the potential things. I still have these leftover operators, so I have to still do the normal ordering according to Wick's theorem of these things. And then I do the same thing with 2 contractions. So I do phi 1 and phi 2, phi 3 and phi 4. And then in this case, I write normal ordering, but technically I could get rid of that because these contractions themselves are the scalar Feynman propagator, which itself is a number, depending on, it's a different number depending on x naught or y naught being greater, or so which is earlier in time. But I just still wrote them in here anyway. So this is an example for Wick's theorem. Now, I don't want to torture you because there's a lot to understand for Wick's theorem, but there's a little subtlety here that gets somewhat confusing, but you can take a moment, kind of screenshot this or pause this and take a look at this. I think it's pretty well explained. Remember in our earlier lecture, for reasons of avoiding infinities, we decided that our interaction Hamiltonian has to be not just phi to the fourth, but normal ordering of phi to the fourth to help avoid some infinity problems. So right off the bat, we're already dealing with normal ordering of our operators in our interaction terms. And it turns out if you look at our derivation for just Wick's theorem with just two operators, we never derived it in generality. It turns out if you have already normal ordered terms, then you don't have to do contractions if you're talking about equal things in time. So if we have phi x and phi x at the same time, and if they're normal ordered, you don't ever have to do a contraction for them. So when we're using Wick's theorem for normal ordered fields that are already pre-normally ordered, because that is our interaction Hamiltonian, then you don't ever use equal time contractions. So the kind of upshot of all this, if you don't want to read it all, is that this is a slight modification of Wick's theorem in the way that we'll always use it. We'll always use normal ordered interaction Hamiltonians. So you can say when I use Wick's theorem for something like this, what happens if x2 and x1 are at the same time? Do I also contract them? The answer is no. We will never use ETCs or equal time contractions. So if you ever see two terms that have equal times, you don't ever contract them. You can contract non-equal times, but you never include no equal time contractions. That is the correct statement for Wick's theorem when you have an already normal ordered interaction Hamiltonian. Now we can start to get back at our actual problem. Remember, we had something like this. I got rid of some of these other prefactors, but we had, when we were calculating our 2 to 2 particle scattering, the time ordered expectation, the time ordering of all of this here. This was buried within, P1, P2, and Q1, Q2, and some other factors, but this was kind of the operator thing that we were trying to struggle with dealing with, this time ordering. Now we're going to use Wick's theorem that we just learned to this expression over here, the time ordering of all of this. Can we convert this time ordering into normal ordering, which you'll find is easy to deal with our formalism? Time order is not easy. Normal ordering is easy. The answer is yes. We're going to use Wick's theorem here to make that easier. Now, we'll have to, because we have a normal order thing, just remember no ETCs. You could just think of that as Wick's theorem. The subtle justification is that we have normal ordering. That's why that's why we're insisting on using no ETCs. That's the correct way of using Wick's theorem in that scenario. So let's apply this Wick's theorem to this expression over here. So the time ordering of all of this over here is just, we're going to do normal ordering of the whole thing here, uncontracted. So we're going to write all of that over here, plus the normal ordering of all possible contractions. So let's do one contraction where we contract one thing with another thing over here, which is what I did here, the first with the first. But here you can also do the first with the second, and so on and so forth, the second with the first, and so on and so forth. And then I have to always normal order the rest of it that's not contracted. So that's why there's an n with these brackets around it. Plus, remember, it's all contractions in Wick's terms, and I have to consider contracting two things. So here I do phi 1 with phi 2 and another phi 1 with another phi 2. And I can mix around these different orders. Then I do 3 things and 4 things and until I have all of it exhausted. So normal ordering of all possible contractions, started with no contractions, 1 contractions, until all the terms are contracted. So that's this here. What's so good about that? Well, there's nothing on the right side that is time ordered anymore. There's only normal ordering, which, as we'll learn eventually in the next lecture, is much easier to deal with. We've already kind of seen that. We have destruction operators that are going to be next to other operators, creation or destruction, but you have nothing about time ordering anymore, and that we know how to deal with. Before I finish this, just mention a couple of big things. We've been talking about equivalent ways of writing a lot of stuff mathematically here, but we need to know kind of all of them, even though it just seems like we're just redefining the same thing. Sometimes it's good to draw diagrams. We're just going to build up to a very important idea in QFT called Feynman diagrams. And I'll just start simple here instead of going into the whole thing. But sometimes it's convenient to draw diagrams to represent a contraction. So if you have an operator phi at spacetime point x1 and another operator phi at spacetime point x2, and we have this thing that we talked about now, contractions, sometimes we just write a diagram like this to represent this expression, where I just take spacetime point x1 and just draw it as a point on my PowerPoint here, or a piece of paper. And I take x2 and I just draw that as another point on my piece of paper, and I just have a line connecting them. And by definition, that means this contraction, which, of course, this by definition we said was this, which is the scalar Feynman propagator from x1 to x2. So sometimes we'll draw a line like this, a diagrammatic representation of this or this mathematical expression. Very convenient and very important. If I have something like this, where I have phi of x1, and then phi of x2, where x2 and x2 are at the same space-time point, x1 and x1 are at their same space-time point, and I have a double contraction, well, I can write that like this. I draw the space-time point x1 and the space-time point x2, and I just draw a line connecting them. And one of these lines represents the first contraction, and the other line represents the second contraction. And that's just this expression by definition here, where I take the first contraction and I just multiply it by this. This ultimately is a number, and this ultimately is a number, so it's going to be a number multiplied by a number, since all of these, this initial expression is just everything multiplied together. So that's what this diagram here will represent, this scalar Feynman propagator from x1 to minus x2, and the scale multiplied by the scalar Feynman propagator from x1 minus to minus from x1 to x2, or that expression is x1 minus x2. Here's just another example. Let's say I have x1, x2, and even this x3 over here. How would I draw these contractions? And I contract this with this, this with this, and this with this. Well, same thing. I just draw my space-time points, x1, x2, and x3. There's three of them here. And I just, every time I see a contraction, I connect the two. So I connect this guy with this guy, x1 to x2. But here's another x1 to x2 connection over here. And then here's an x2 to x3 connection over here. So this whole thing would be equal to this over here. If I do these contractions, this term times this term times this term, which is the scalar Feynman propagator from x1 to x2 times the scalar Feynman propagator from x1 to x2 times the scalar Feynman propagator from x2 to x3. So this diagram represents all of this here. And these things, just remember represent terms, numerical complex number terms, that you have to actually represent an integral, but the whole integral will end up being a number. Now, thus, we have learned that instead of dealing with time ordering operators, we can deal with the much easier normal ordering operators, but we still also have these contraction terms, which are these scalar Feynman propagator terms. And here I'm just re-expressing things. Recall that what is the scalar Feynman propagator? Well, it itself is either one of two expressions, this one over here, which ultimately will evaluate into a number, dx minus y, or this whole integral, or this number here, depending on whether this original, which time it was first, x naught or y naught, this or this. So it may seem like we've done a lot here, but someone that's following and just realized we added just a bunch of names for the similar things may realize we haven't simplified our problem that much. We got rid of time ordering operators and change them to normal order, which we like because we can deal with normal ordering operators with this A and A dagger formalism. But hidden still, we have these contractions, and these contractions are in there when we switch to time ordering to normal ordering operators. But even though we're saying they're just numbers, they're really one of two different numbers, depending on whether x naught is greater than y naught or y naught is greater than x naught. In other words, we still end up dealing with the time dependence thing. We just hit it with all of this expression. The way we've written it, we still have like this binary expression where I have to use the top line if x naught is greater than y naught, but this bottom line if y naught is greater than x naught. So we're still kind of hiding this time dependence in just this symbolism. However, the big thing is that you can actually re-express the scalar Feynman propagator as a single mathematical expression, not two ones depending on what time came first. You can express it as a single mathematical expression, delta f. And that'll be the subject of the next lecture and our purpose. And we need to deal with some a little bit more complicated and maybe unfamiliar math, complex analysis. But that's what we're going to show in the next lecture. That even though we just use Wick's theorem to convert time ordering to normal ordering plus scalar Feynman propagators, the scalar Feynman, even though it has two expressions here, we can actually do some mathematical tricks and make it a single mathematical expression that becomes a lot easier to deal with than original binary things that happen when time ordering.